Krabbendam. I am the project manager for LSST. And I'm holding this in my hand because this is day 4 of a collaboration meeting that we're having here at the hotel. And so we have about 250 of our project members and community colleagues that are here collaborating on what we're doing to build LSST and how we're going to use it. And so it's really nice to be able to spend the evening with you and talk a little bit about what we're up to. I think our format is going to be a little bit of a motivation for LSST, and then a few anecdotes about how what we face when we're building it. We'll at the end refer you to a lot of information that's available on websites, and we have people walking around with these kind of tags, and they would be available for any kind of conversation, as well as afterwards there will be some people gather around outside to take any questions as well. So, as I said, we've been here all week. I just want to take a moment and thank the Westin for really providing us some great venue, and the staff here has been excellent. And so hopefully tonight will be no different than the way we've been able to work all week. Here we go. So before I get started too far into what we're doing, I wanted to show you this iconic image, which is sort of what we think about when we think about an observatory. A nice building on top of a majestic mountain. But for LSST, and before we get too far into it, I really want to point out that we are much more than just a nice telescope on a beautiful mountaintop. LSST is really about constructing this facility and then conducting a 10-year survey. That's to take the data, process that data, archive the data, make that data available as either individual images or data products. And so when you look at this image, what you see is that we talk a lot about what we're doing to build a telescope, and that's an 8.4 meter class telescope. We're building a gigantic camera, which has got 3.2 gigapixels. And then we have what we do with the data, and that's an extremely important part. When you're generating as much data as we do, we have to have what we call a data management system, and a petascale data management system because of the amount of data that we are producing. And you'll see along the way, we'll talk about things like 15 terabytes a night and 500 petabytes over the years that have to be dealt with. And so data management in this case is extremely important. And lastly, we have to be able to provide that data out to the public and to our constituents. And so there's a very big and important part of the project, which is the education public outreach and the regular science interfaces. So that's what, when we talk about LSST, it's all of those things. Also, before we get too far, I wanted to point out our funding partners and acknowledge that the NSF, the National Science Foundation, has supported the project with a not to exceed amount of $473 million for construction. The Department of Energy has contributed $168 million and directed at the camera. And we had a great start, early start from our LSST private corporation, which was instrumental in raising, it's really supposed to be $39 million, already third chart, it's already in the state. And so in total, it's about $680 or so million that are going into the construction of this facility. And so one of the most common questions I get when people see especially this kind of a chart is why? Why are we spending $600+ million for another new astronomical telescope? And so to talk a little bit about that motivation, I'm going to invite my good friend Dr. Chuck Claver up, who's going to talk a little bit about the motivations and why we are building LSST. Thank you, Victor. Good evening.
So why are we building LSST? Victor said it's $600 million is an awful lot of money. And from my perspective, one of the reasons why we are building LSST, because scientifically right now, we're living in some very interesting times. And by that, what do I mean? We know that through images like this, where you see the distortions of background galaxies being warped by the foreground galaxy due to gravitational lensing. And you see a couple instances here from the CFHT and the Space Telescope. But what this tells us is that through these images, that most of the matter that is in the universe is dark, because the luminous matter you see on these images cannot account for those warped images. We also know that through measurements of something called a Type 1a supernova, which is an exploding star, and what's nice about it is that they always explode at the same brightness, so they can be used as what we call a standard candle to measure distances, and when you go into cosmic distances, you're also looking at time. So the upper right image there shows just such a Type 1a supernova in a relatively nearby galaxy. And then if you plot the brightness of the supernovae against their distances and the look-back time, you get this plot here. This is one of the plots that led to the discovery of the accelerating universe. And if the universe was not accelerating, all these supernovae out here would not be above this bottom line. They would lie on that line. And this led to a Nobel Prize for a group of astronomers in 2011. And the thing when you accelerate something, it requires energy, right? So you need energy to accelerate something. We don't know what this energy is. So if you took the total mass energy content of the universe, so you can equate mass and energy through Einstein's famous mass energy equivalence equation, E equals mc squared, we find out that we call it dark energy for the lack of a better phrase because we don't know what it is. And there's this thing that the thing that's responsible for the warping of those galaxies is cold dark matter here. That constitutes 96% of the mass energy content of the universe, and we know nothing about it. So that's going to be either very depressing or also very exciting. As a scientist, find it very, very exciting because the potential for discovering something profound is extremely rich right now in research. There's a whole bunch of projects out there that are tackling this problem, and LSST is one of the premier projects to do so. But we know a little bit more about our universe than this picture might portray. We know that the Earth, as it orbits the sun, actually is plowing through a debris field of asteroids. And every now and then, one of those asteroids gets in the way. This is the Chelyabinsk event from, I think, 2013 over Russia. And these things happen, right? This is one of the first events since the Tunguska blast where there was physical damage on the Earth caused by an asteroid passing through our atmosphere. But the thing about this is that we have, these things happen, we know they happen, we see them relatively frequently, not at this scale, but we very rarely, if ever, have any advance warning. And there is a real probability that there are asteroids out there that are big enough. If they were to hit the Earth, they would not be a good day for us. And so LSST is aiming to try to give us some advance warning of some of these potentially hazardous asteroids. We also know through various experiments, both on the ground and in space, in this case I'm showing you a picture of the Kepler mission, that nearly every single star in the Milky Way varies their brightness in some way, shape, or form. And yet we don't know much about why this happens and how these stars came to form the Milky Way. So there's a number of questions out there, and so how do we answer them? How do we answer some of these big questions in science today? And I'll say that significant advances in how we think about the universe have often come on the heels of discoveries in technology. And these new technologies, when applied to, in particular, astronomy and our observation of the universe, often cause a paradigm shift. And the Large Synoptic Survey, I believe, will cause such a paradigm shift. We just aren't quite sure what that shift will be. So LSST is a survey machine. We know from past projects that survey, the title of the talk is The Next Great Science Engine. When you survey the night sky, it generates the raw data and the raw material to do amazing research, and it really just is the engine for a lot of different kinds of studies. But I want to put LSST into context and kind of walk you through some of the history connecting all sky surveys and some of the technologies that led to significant advancements. So starting pretty much since man was conscious and was looking up at the night sky, we've been cataloging what we see up there. And this slide shows just a handful of examples of some early sky maps from the Egyptians in 50 BC, to Chinese charts from the 1st and 2nd centuries, and then a Dutch chart here from the 17th century. And all four of these examples have one thing in common, that the detector used to create these charts was none other than the human eye. That was the state of the art from pre-Christ era all the way up to through the 17th century. And this cataloging by eye continued even beyond the 17th century, all the way into the mid-19th century when a discovery was made. And that discovery was something called silver halide. Now, a lot of the younger people in the audience may not know what silver halide is or how it's used, but silver halide is what was used when put on either plastic or glass to create photographic plates or photographic film. A lot of us here still remember doing photography that way. And that entered the age of photography, and then with using photographic plates, we were able to take the next step in understanding the night sky. So here, I showed you an example. This is John William Draper's photograph from March of 1840. This is the very first astrophotograph that we're aware of, and it was a photograph of the moon. It's a little hard to tell, but this blob here is the moon. But yet it took 100 years after that first photograph of the moon before technology caught up to this discovery of silver halide crystals and was able to start putting down high precision emulsions on glass plates. And then when you combine with that technology, specially designed machinery, instruments like the Schmidt telescope at Paloma, then you enable the next phase or the next class of sky surveys. And so the first Palomar sky survey was completed in 1958, and you just see an example of that here. And that really opened a new pathway to new discoveries about what the universe looked like. About the same time, just a few years prior, the first, what I would call digital sky survey was done. It was done by hand. And what Shane and Bertanen did in 1967 is they took 1,246 photographic plates. They were 17 inches by 17 inches. And they literally put down a grid that was 10 arc-minute squares, and one by one, by eye, they counted the galaxies in each square and then made a plot of the density of galaxies across the entire night sky. And this led to the discovery that we live in a clumpy universe. This was new. And it took some, more than 10 years to be able to do this by these two people. And it was finally published in 1967. And to give you an idea where we are today, there's this thing called Galaxy Zoo that has been part of the citizen science programs, that the equivalent analysis can be done by the suite of Galaxy Zoo users in about less than 10 minutes. So the photographic plate was still the state of the art all the way into the 70s, but the machinery to evaluate the photographic plates evolved. There's this thing called an APM machine, the automatic plate scanning machine. And with photographic plates, you can customize the emulsions to be sensitive to different colors, using different filters. And this allowed people to replicate that first galaxy count, to produce a galaxy count with colors. And now, not only do we learn that the universe is clumpy, but that clumpiness has depth because color is related to distance. The next big discovery or invention that came around was this thing called a charged bubble device that was invented at Bell Labs by Boyle and Smith. It was originally designed as an analog delay circuit, so that a signal would come in on this side, it would go through these little charge plates, and then they'd come out on this side, a delay. And as they were doing their experiments in the lab, they kept coming across this noise that they couldn't figure out where it was coming from. And they eventually figured out that the noise was coming from the fact that light was hitting this array and depositing, converting the photons into electrons. And this led to the discovery of what then became the charge couple device as a shift register. And then there's this funny named company called English Electric Valve Company. Some of you in this room may know that they are now called E2V, who are responsible for a large number of CCDs in astronomy right now. And they invented the first CCD video camera, and then at Kodak, they came up with the first still camera using a 100 by 100 pixel Fairchild device. And then only a year later, the first reconnaissance satellite was launched with an 800 by 800 pixel CCD. And this is the first astronomical CCD image taken with one of these Fairchild devices. And it's hard to tell because the volumes are so low, but this is also of the moon. So the first astronomical image with a CCD was used the same object as the first astronomical image with the photograph. This led to producing arrays of these devices. This is a first generation of mass-produced CCD. This is an RCA CCD. This is circa 1980. They were small, they were noisy, they were really expensive, but they were very sensitive. They were almost a factor of 100 times more sensitive than a photographic plate. And unlike photographic plates, their responses to light was nearly linear, or very close to being linear. So this was circa 1980, and it took another more than 10 years, almost 20 years, before the technology matured enough. And then again, you're seeing the coupling of new technologies being mated with specially designed machinery to enable large sky surveys. So here we have the Sloan Digital Sky Survey camera with its multicolored focal plane. Here's the telescope. So this telescope was designed specifically to take advantage of this large focal plane. And so this enabled a new linear digital age in all sky surveys without the need of scanning photographic plates. And these large cameras now rival what was able to be done with a Schmidt telescope and those glass plates. So up until the last 10 years or so, the Sloan Digital Sky Survey was effectively the state of the art in optical surveys. Here you see the all-sky footprint for the North Galactic Cap and the South Galactic Cap from Sloan Digital Sky Survey 3. Here's some examples of the dynamic range of the imagery that comes from the Sloan Digital Sky Survey. But I want to point you out, right now we're in the middle of SDSS-4, but the common thing between all four of these programs with SDSS is each one of those takes several years to do. And so while this is an incredible wealth of information about the night sky, it is relatively static. So we do know things about the night sky. Our night sky is not static, right? If you could look up in the night sky and see all the type 1 supernovae going off in a year, the night sky would look something like this. Right? So this is just an animation simulation. And if you had some magic eyes or a magic machine and you could see all those supernovae, this is what we would see. So we know that there's time-dependent behavior on the night sky. Similarly, if you could see all the asteroids on the night sky, it would look something like this. And so what you have here, these are your main belt asteroids, and occasionally you'll see one of these little yellow things come zipping by on some weird angle, weird trajectory. These are the nearest asteroids that, like the Chile asteroid, that we tend to worry about. And there's other kinds of variability on the night sky. There's tiny shifts of the stars wiggling back and forth caused by parallax as it orbits the sun. There's proper motion of stars because the stars actually do move. You may not know that. And there's all kinds of interesting things. Even the supernovae, there are other objects that flash in the night. And we just don't have a really good catalog of all these things that change on the night sky. So what if we could discover and observe everything that changes? What if we could build a system that could digitally record the whole sky in a matter of days? Instead of taking a couple of years to do it, we can do it in just a few days. And if we could do this over and over and over again for years on end, we could build up this knowledge and this understanding. And what if we could look deep, fast, wide, all at the same time? So it comes in the answer comes from some imagination, some dreaming, some thought, some invention. And I met Tony Tyson and Roger Angel on the same day, shortly after I moved to Tucson. And at the time, Tony was thinking about an all-sky survey to explore dark matter, to better understand why most of the matter in the universe is dark. Roger Angel, at the same time, was thinking about how can I build a wide-field 8-meter class telescope that could survey the night sky. So there was a nice superposition of these two dreamers at the same time in the same place that led to the start of LSST. And I got involved in 1998 when I was asked as a young scientist, can we build this machine? Is it possible to build something like this? And so, in the early 2000s, the LSST project began to form. So, we did some studies of various configurations. We understood basically how to build 8-meter class telescopes. We looked at sensor technologies, and it's the technology in principle was out there. Reality is that it's harder than it may first appear, but it's certainly doable. And even though computers of the day were not sufficient to process the LSST data that we were envisioning, there's this thing called Moore's Law, and we figured that by the time it got built, we would have the computers available. Sorry. But so at this point in time, as the project was forming, we had to go beyond just a few people in Tucson and a few other places that were thinking about how to build this thing and how to design it. So we started forming the engineering team to build LSST, or to start designing how we would build it. And at the time, I was asked if I knew somebody named Victor Krabbendam, and whether or not he would be good to lead this engineering team. And I said yes, and that was based on that 10 years prior, Victor and I happened to have crossed paths. I was a grad student in Austin, Texas, at the University of Texas. Victor was an engineer building the Hobby Evergreen telescope. And it's interesting that our paths have crossed again, and this time instead of crossing, we kind of got stuck on the same train. And so I'm going to give it back to Victor here, and he's going to walk you through some of the technology. So again, remember, this is about taking inventions and then applying them for a specific design for a specific purpose. And you'll see that LSST is a one-of-a-kind machine. So Victor.
Thanks for saying yes, Chuck. So one of the great things about being able to build telescopes is that you can actually collaborate with scientists that have dreams like this. And so once we start actually making that collaboration happen and starting to think about what the engineering really involves. And you saw those first two images of different kinds of telescopes. Now it's about how can we really make this efficiently, make this in a reasonable cost and schedule. And so one of the first things that we did in collaboration was to think about that optical design. And if you noticed in that initial napkin, that was an optical design drawing. And it was this long, that's what we call the long tube design. And the secondary mirror was way out here, and the tertiary, where there was mirrors really far apart, the camera was in the middle, and it was going to be really hard to build a structure for that. And so one of the real first objectives was to figure out how we can make the same optical design, the same performance, but something that we could build. And so what you see here is that optical design. And if we just go to the next slide, you'll see how those mirrors looked. So if I'll go back again. There's a primary surface. I have the device. There's a primary surface right here. There's a secondary surface up here, a third, and then the light goes into the camera. And so if we look at that in sort of a 3D image, and you look at how that light is going to traverse, it would be in that form. And one of the things, we'll do it one more time, one of the things that's really critical is that this camera is right in the middle of the optical path. And so that puts a lot of challenges on that particular device and how compact it has to be and how careful we have to be about it. So that was successful. And then we get to the next part, which is, okay, now we have a design for optics that will work. How are we going to make those optics? And luckily, the U of A, not luck, but as it so is, the University of Arizona had already been developing 8.4 meter mirrors, had already done a few demonstrations of such, and built, for example, the Large Binocular Telescope on Mont Graham with 8.4 meter mirrors. And so we knew that existed, but we had this interesting situation where our third mirror was now designed to be very close to our first mirror. And so we did a particularly long study and a very careful study because never before had anybody tried to put two massive optical surfaces that are precise to less than the thickness of your hair in one substrate. And so after that very long and detailed study, we decided it was doable and embarked on that fabrication process. And I'm happy to say that several years following, I think it was somewhere in 2009, somebody can probably help me there, we finally finished that optical polishing activity. And this is an image of that mirror in the mirror lab right here at the University of Arizona. And you can see there's the tertiary mirror, and there's the primary mirror, and it's one gigantic 17-ton piece of glass. Now, one of the interesting challenges that we face when we build things this big is you have to move it around. And there's no place to store that kind of a mirror of that size for many years in the mirror lab, and so it had to go. And here's an image of what it looks like when you move. Basically, it's 100 tons of material running down the road between truck and glass and its crate. But you have to move it, and you do things like move it at 4 in the morning when there's nobody else around because you take up a lot of space. Even though it was a mere 8 miles down the road, this was a very large engineering endeavor and a very big logistics endeavor, just to get it down to the airport where we could store it, where it still sits today, waiting for us to build up more of the hardware. Because what it takes to make a mirror is more than just glass. And here's an image. This is the glass rendered here in some shading around it. But what it takes to make a mirror, and to make it functional, is an incredibly large number of actuators and springs and mechanics, air systems, moving air inside, have to equilibrate the glass. And all of this is tens of thousands of pieces. It's also, sorry, the clicker is slow. It also requires an incredibly stiff backbone. And so if you pulled apart that steel structure that's below the glass, and you recognize that some of the requirements on it are that the thing can't deflect more than about 1 millimeter or so when it's under load, because it's under load in the telescope, the glass is going to different angles, And it also has a particularly difficult task of being part of a vacuum chamber when we have to coat this mirror. And so it has to go through these different types of stresses, and so you get just a sense of the complication that's involved in making that what might appear to be a fairly simple steel structure, albeit large. That steel structure looks a lot like this today, and is also being built here in Tucson, down by the airport at Cade Industries. And has been successfully machined and is very close to being ready to be populated with all of that equipment. What we plan to do is, after it's been populated and it's been turned into the assembly that we need it to be, we're going to marry the glass and the structure back together again and bring it to the U of A for one last test of all of that mechanics and all that glass together before we ship it all down to Chile. So that's, you've heard Chuck talk about having to go fast and wide and deep. A big mirror gets us deep. And now we need some more requirements from our fellow colleagues in the science community for how we do the rest of the telescope.
So, Victor just said, so we have a big chunk of glass. The collecting area of the telescope, of course, allows you to go deep. So that's one part of the equation. So we have two parts to go. So our goal is to go deep, fast, and wide. Why fast? Because as we said, we want to cover the night sky every few nights so that we can start building up that time history and start understanding those things that change in the night sky. So what we've been doing over the last several years, or during the early years, we ran some simulations here trying to figure out what is it going to take to cover the entire available sky in a short amount of time. And we arrived at, you can go, there's usually a sweet spot, and or if there's not a sweet spot in the capabilities you're seeking for, you usually start coming up on some boundary limited by technology or other practical matters. In this case, our simulation showed that if we could slew and move the telescope one of its field of views away to an adjacent field, and do that in about 5 seconds, we could actually cover the entire night sky in roughly 4 nights. This is the kind of quick coverage that is necessary to get at some of the time-dependent behavior we're after. And recall that the Sloan Digital Sky Survey required several years to cover the entire night sky. And we're doing it in 4 nights, and then that allows us to do it repeatedly over time. And just to give you an idea, this is what a simulation looks like. The little black dancing dot there is the pointing of the telescope. You can see the night sky slowly rotating around, and I believe here one night is about 30 seconds in duration. So what you saw there was about a half a night's worth of observing. But this is the kind of simulations that we've been doing that has led us to put design constraints and design requirements on the next part of the puzzle. And Victor will talk about how you convert those speed requirements into something that will realize performance.
And so the summary of those requirements that come from our dear colleagues is that you have to be able to go do 15-second images, and in between each images you have to be able to read out in about 2 seconds. And then after you've been on one place in the sky for 30 seconds, as Chuck says, get 3.5 degrees away, and from the time you close the shutter to the time you open the shutter, you have 5 seconds. And that takes quite a stiff structure. And so if we look again at our optical design, but you look at it sort of tilted, and you then think about, well, how am I going to keep all of those optics stiff and accurately positioned and move as quickly as we want to be efficient, you get to a structure that looks a lot like that. And so there's the structure wrapping around all the optics. The good news is that optical design, remember early on we made it as compact as possible, And that really helps us because this particular telescope turns out to be sort of shorter than it is wide, and that helps a lot in being able to move as quickly as we have to. So we have roughly 300 tons of moving structure, and we have to have the stiffness to get it optically lined. And to meet those speed requirements, we're running at around 10 degrees per second of speed and 10 degrees per second squared of acceleration, because you have to take that entire structure and move it at 3.5 degrees on the sky, which can double in terms of distance in the azimuth direction. So right now, we are actually in the process. It's been designed. We have a contractor in Spain that's well on its way to developing the mount. And what you see here is the trial assembly of that structure in one of the fabrication houses in Spain. And this is one of our theories is to spend as much time while you're close to the shops, while you're close to the design house, to do the testing and to build these things up so you can test them as completely as possible before you take all of that hardware to a remote mountaintop where it's going to be much harder to build. So right now you see a bit of the structure. When it's all done, it'll look a little bit like that. And one of the interesting things to think about is when this telescope is rotating at its 10 degrees per second, it's basically going past you at 20 miles an hour if you're standing next to it. And so it's going from 0 to 20 to 0 in 5 seconds. And to do all of that takes an incredible amount of power. And as you can probably imagine, that there's also a dome. And when you look at the power required for the dome and the power required for the telescope, it takes about 2 megawatts to make that move. And that would put a tremendous drain on our electrical grid. It's about the amount of power it takes to run 1,500 homes. And so to combat that, and to make sure we don't drag the whole power system down and affect our neighbors that are also interested in keeping the lights on, we do things like putting gigantic capacitor banks. And these are banks and banks of capacitors that are built into the bottom of the telescope that just constantly draw power. And it reduces the amount of power on the grid down to several orders of magnitude lower. And therefore, we can instantaneously get the power we need, but not draw down that instantaneously on the grid. So this is well on its way. We're very excited to get this telescope in the shape that you see it here, and to be able to start moving it to the mountaintop. So there's fast. Now I invite my dear colleague to tell us about why.
So, one of the unique features of LSST is its wide field of view, and it's enabled by that 3-mirror design. That's what most telescopes, most professional astronomical telescopes utilize 2 mirrors, but the degrees of freedom or the ability to optimize that optical design with only 2 mirrors limits the field of view that you can actually have without a lot of correctors. This gives you, this is an example of what really sets LSST apart from most other professional telescopes. So here, what you're seeing, the Gemini South telescope, the blue disk, shows you its primary mirror, schematic of its primary mirror, and the shaded blue area is the collecting area for photons. And you see its field of view over here is a couple things of a degree of diameter. LSST, on the other hand, this shaded blue annulus is its collecting area. Remember, the darker blue is the third mirror. But this is a comparison of the field of view to scale. So LSST's field of view is 3.5 degrees across. It's enough to capture 7 full moons across the diameter of the focal surface. It's a little hard to grasp exactly how big that really is on the sky. This is a beautiful photograph of Orion's Belt. You see the Horsehead Nebula here. These 3 stars and this star, these are easily recognizable when you see the constellation Orion. They're naked eye stars. And if you were to superimpose the LSST focal plane on top of this part of the sky, it would do something like that. So next time you're out in the night sky and you see Orion, you look at Orion's Belt, you can really capture exactly how much field of view LSST gets in one picture. It's really quite amazing. And it's this last third bit, when you combine the aperture of LSST, the speed of the hardware, and its wide field of view, that's going to enable this time domain survey that we're talking about. But behind this focal plane here is a very complex instrument, and we call that the LSST camera. If you were going to walk you through with that.
So it's only the astronomy's largest digital camera that's required for LSST. And it looks a lot like this. If you cut a quarter of it out and you sort of looked into the inside, you get to see just how densely packed and how much mechanics, electronics, and utilities are required to operate this telescope. And so just to get a little sense of scale, if you were 5'5", then you'd be right as tall as the front lens. I think that's the average height of the U.S. woman, I believe, something like that. And so you're looking at a gigantic lens, and you're looking at over 3 tons of material that's required, of electronics, of structure, and glass to make this camera. And deep into the heart of it, of course, is what we really need, which is that focal plane, which is those CCDs that actually have to convert the light into electrons. And that looks a lot like this. If you just pulled away all of the material, and you might recognize that the image that Chuck showed a few minutes ago had sort of that grid pattern, and you see that was what was actually imprinted on his image. So this is 63 centimeters across, and it takes 189 1-inch by 1-inch sensors to fill that aperture. And the way we do that is we take 9 of them at a time, and we build them onto a raft, and the electronics that supports all 9 of those sensors are designed and built in a way where it fits right behind the footprint of those 9 sensors. And so you can build an array. The entire science array is just 21 rafts identically built. And so this is a significant challenge. These sensors are all custom for LSST, and I'm happy to say are well on their way to being fabricated by two different vendors. And here's just a couple of images. This is actually one of the first raft tower modules. Those sensors, this is upside down, the sensors are here, and this is all of those electronics required to convert the optical signal into an electronic signal. And there's a couple other images of what the front sensors look like on the front plate. Now, if you're familiar with many astronomy cameras, you know that sensor delivery is a significant risk and is usually one of the tall poles. And I'm happy to say that with these 2 vendors delivering sensors, that we're already, in fact, with this week's deliveries, we're already beyond 39% of all of the sensors that we need to finish this camera. Now, the other interesting and difficult part is that also for efficiency, we're always trying to collect all of those photons. And so you saw how closely packed all of the sensors were. And that becomes a bit of an engineering challenge, not just in building each individual raft, but just how you're going to insert rafts next to each other. Now, these are think about this as the extremely delicate pieces of glass. Very thin, they're actually electronics. You can't touch them with your hands, and now we need them to be spaced microns or 0.5 millimeter or so apart. And if you thought about this car, if you thought about a car, you have to be putting them between each other with about 1/4 inch of spacing. And you wrap that down to something that's only 3 inches across. These things are extremely tight. And so one of the exciting parts about building an instrument like this is that you have to invent machines to actually do the production of the product that you need. And so this is just a nice little rendering of just how difficult and the kinds of challenges that we face. And of course, let's also be clear, this is not $1 million worth of car, but this is over $1 million worth of sensors. That one rack. A couple other things that are well on their way at this point. And I point these out because this is some of those lenses, the 1.6 meter diameter, 5'5" diameter lenses, that are also being built right here in Tucson at Arizona Optical Systems. And so here you can see that lens in production, another lens, L2 in test, and the custom carbon fiber structure that's required to keep those two together. Because this particular assembly, if you remember what the camera looks like, that is sticking way out in the front. And it's all about how stiff things are and how accurately we can keep those optics along. And so this is also well on its way, again, right here in Arizona. So one of the other things that's required when you build a facility like this is a massive telescope, lots of electronics and glass and lots of custom items, is you just have to surround it with all of the infrastructure necessary to run it, operate it, maintain it. And so if you thought about the camera, the telescope that we've been looking at sitting on the mountaintop, and you then thought about all the structure that's required to surround it, protect it from the elements with the dome, you need a slit to be able to look through it at night, and you need very stiff structures to hold onto it. We put it up high enough so that it's out of the wind and some of the lower layers of air coming across the mountain, and you need lots of facilities to handle this large optic, this big camera. And so you just start to add all these things up, and you get to the point where you have a very, very large facility. You also have to surround it completely if you thought about the whole building, and it starts to look a lot like this. One of the questions you get is, well, why did you make the LSST? This looks like a ship of some sort. And it comes down to a lot of engineering. This is not just what we thought would look good. It was a lot of computational fluid dynamics, because one of the things that we actually don't like in optical astronomy is that there has to be a building. If we could get rid of the building and just leave those optics there in the free air, that would be the absolute best. And so you have to start engineering around it. And so what you see is a lot of energy going into, a lot of time and design going into how we get air through that structure and how the air is going to pass over the building. And that's where this computational fluid dynamics comes from. And here's just a couple of images. If you can imagine, this is the air coming across this part of the building. If we didn't have some of these deflectors, it develops this turmoil, and that's sort of this red showing there. And if that were not air that was the same temperature as everything else, it literally is boiling over the top of the structure, and we would see that in the optical image. But with the deflectors, everything goes over much cleaner. And so you start to see that it does actually look pretty cool, but it's also there for the aerodynamics. So what does it take to build a telescope on a mountaintop? Well, you got to do some early site work, and for us, it was pretty exciting. In fact, this picture was taken by Chuck, and it was one of the images of the amount of blasting it took. You have to clear enough space to put the building, and all of that went really quite smoothly. And one of the good things about Chilean culture is that you don't wait till you get the building built. You actually start right at the get-go, and you have a ceremony for laying the first stone. And so very early on, before we were too far along, we had a nice ceremony with the president of Chile, the director of the NSF, ambassador to Chile as well. And so that was a wonderful way to start the building of our over 4,000 square foot building on this mountaintop. And I am here to tell you that you can face a few challenges. First of all, when you do start doing a lot of the digging and the detailed digging, and you realize that it's not rock everywhere you thought was going to be rock, that you end up digging and digging and digging until you find rock. And of course, we spent a lot of time testing where the telescope is going to be, making sure that was solid rock and it was great, it was solid foundation. But over here where the building was going to be, not so much. And so we had to dig a very, very, very deep swimming pool. It took 6,000 cubic meters of concrete to fill up that hole after we dug it. But eventually, it does get filled in, and it looks a lot like this. This is a 6,000 cubic meter foundation of concrete. The other challenges that we face on this, on a mountaintop is weather. And for whatever reason, LSST was struck in the very first season and in the next season with some of the craziest weather that we get. And so one of the storms of the century came through. There's our site, the coastline of Chile, and we happen to be trying to build during that period. And so you deal with things like rivers suddenly forming on your mountain road, and cars getting stuck, lots of snow, and all we can do is just keep working. And we've done that for 2 seasons now, 2 winter seasons, and I'm happy to say that the building is actually progressing and looking quite a lot like the image, the rendering is. So now we're on a mountaintop, and we're about to put all of this, this very large telescope, this extremely expensive and very high-end camera, and we're going to start taking all this data. Now what? Well, that's where the data management system comes into play. And so we have to be able to, when we talk about data management, and I mentioned it earlier, you have to sort of take all that data and do something with it, and that's what we call sort of the algorithms. There's a lot of processing required to take a raw image and turn it into even calibrated images that we can use it individually, or to make data products so that we can catalog all of those objects that we find. And then you have to store that data. You have to be able to store it in a way where you can actually harvest the data and the information afterwards. And so that's where database technology comes into place. And again, this is gigantic. This is big data. This is 15 terabytes coming off that mountain every single day, every night of operations, and it builds up over the years, over a 10-year period, because we keep saving all the data and reproducing and reproducing. And so one of the other challenges, of course, is you're on a mountaintop in South America, and our computer center is in central Illinois, and we have a lot of data to get there. And so what we've been putting in place is those lines. And some of it had to be put in place by us, and so we had to actually put those fibers in, and this is sort of down at the lower part of our property, and there is our site. It's about 40 kilometers of new line that we had to put in, but luckily we also were able to take advantage of some of the infrastructure already in place or being developed in South America to actually make the connections all the way to Miami and then up to central Illinois. But to do that, one of the things that Chuck would also like to have is when we see something go bump in the night, he wants to know about it very soon. In fact, he wants to know it within a minute. And so every time we take an image, we actually have to compare that image with the standard image and say, oh, that's different. And so that means we have a minute to take all the data, move it up to Illinois, run them through the algorithms to decide if there's an alert. And to do that, we have to make sure that it's not just a fiber optic coming off the mountain and that those networks are there, but they're really good networks. And so it turns out that what we have in place is 2 100 gigabit per second fiber optic connections. It's a protected network, so if one side goes down, the other side picks it up. But that doesn't mean much to me either, so don't worry. But I did do a couple of comparisons here and to look at what that means. And so if you took the entire Lord of the Rings trilogy, it would take a second and a half to move all of that in high definition across from Chile to Illinois. If you like movies, or if you like to stream music, then we can do that at 4G simultaneously to 2,000 cell phones at once. And lastly, it takes 1 second for a single image to move, a single one of our images to go from Chile all the way to central New York, or central Illinois. So one of the last things that we wanted to cover is the element that we're also actually it's uniquely part of this project in a way that's not ever really been done in construction projects. And that is that we are able to put in place and be thinking about an education and public outreach program early, while we're building, while we're designing the whole system, thinking about what it's going to take that data and actually deliver it to the public in ways that they can actually use it, whether it's classrooms or citizen scientists. And so this is a part of the project and will allow you to be involved as we get into operations. And so there's sort of three main parts that we point out is sort of the citizen science element and the ability for the public to be able to view the imagery that's coming off the telescope, and actually to even engage as amateur scientists or professional scientists in ways with that data that's really unprecedented. And so we sort of capture it in 3 slides. Your ability to participate. And so here's some examples of Zooniverse, which is a tool, an organization that puts a lot of citizen science opportunities out on the web. And we too will add hundreds using our data sets and really meld them into ways where you can coordinate, you can collaborate and engage and participate. And then exploring by being able to take the data that we're taking off the telescope every night and putting them into tools in ways that you too can keep up with what's happening in the night sky. And lastly, just the ability to discover. And that amount of data, it is not trivial to be able to make it informative in ways where all of us can be, it can be using our iPads and our internet connections to be able to engage and make our own discoveries. So lastly, what I wanted to point out in the last few minutes of our hour is that Chuck and I have been up here telling you about a few of the things that LSST is building and what we're trying to build and why. But I really want to point out that we're representing a very, very large team of people, engineers and scientists and administrators and technicians, that it takes to do all of the work that we've had the honor to talk to you about tonight. And this, of course, is over 250 people right here at the Westin for our week, our conference, taken just a few days ago. But it's really an honor to be able to work with all of them. And hopefully a few of them are still in the audience and haven't actually gone on the pilgrimage to the great solar eclipse, which is happening in a few days. Chuck, close it up?
Sure. So you've got quite a tour of the why we're doing LSST, what it's about, how we're building it, what the sense of the construction effort is. And I want to come back and kind of sum it up by saying that you saw the 3 elements: wide, fast, deep, how the various technologies are being applied to realize that capability. And at the end of the day, we're going to end up with an unprecedented survey that after 10 years, we'll have something like 5.5 million images of the sky. We will have cataloged 20 billion galaxies and 17 billion stars. This will be done with a set of 6 filters. These are colored filters, if you will, that allow us to discriminate the properties and the types of objects that we see. And the time domain aspect of this, we'll be producing something like 10 million what we call transients. These are events of something that has changed in brightness, 10 million of those per night. And then because we're repeating every spot on the night sky roughly 1,000 times, this will allow us to do statistical analysis on the data to produce ultra-high precision, ultra-high uniformity, and very well calibrated data like we've never seen before, which that in and of itself will enable new science going forward. So we appreciate your attention tonight. Thank you very much. And Victor and I are very much looking forward to things really getting started in the not too distant future now, in 2022, when our survey is started. Thank you very much.
So we are available for any questions. I think maybe we'll turn some lights up, and I believe that there's some microphones hanging out in the aisles if you're interested in asking any questions.
Yeah.
Yes, sir.
You mentioned about how you're handling these enormous amounts of power with this big mass. And I believe you said you were going to store it in huge capacitors. Would that also be used just to store solar energy for solar uses rather than lead-acid
I believe the short answer is yes, it can store energy. The trick is that these are designed in ways that you can take in the energy at a different pace at which you can exit the energy. We need it immediately. And so, yeah, it works well for us. It would work well for storing energy in many different ways.
Another question, Andrew?
There's a microphone.
Or you can shout.
Thank you, John. The telescope accelerates and decelerates very rapidly. Will you recover energy when you decelerate, put it back into capacitors?
Yes.
About 95% efficient. Other questions? In the front row.
You showed a picture moving the initial satellite, the mirror from the university out to the airport at 4 o'clock in the morning.
Yes, sir.
How are you going to get up that hill?
Carefully. The question was, the gentleman noticed that we were moving the mirror at 4 in the morning and it was only 8 miles down the road. But last I checked, Chile is something like 6,000 miles away. And so we actually do it the same way. That container is designed. It protects the mirror thermally, it protects it vibrationally. It's actually got a secondary support system within it. And that's going to go on a truck. It's going to get trucked to Houston, and it's going to go onto a ship. It's going to go through the canal. It's going to go to Coquimbo. We're going to pick it out of that ship, and move it up the hill on another truck. So we have actually spent, in the years that we've been spending thinking about how to build the telescope, we have actually been monitoring what the road conditions are. And we do know that there's a couple of pinch points that we have to design everything smaller than, because it's called a tunnel. Okay. It's not a lot we can do about that. But otherwise, yeah, there's going to be utilities we have to move. We have to move a telephone pole here or there, because it's a big piece of it's a big article to transport across the public roads. But it's done.
Sorry, there's another question, gentleman over here.
Perhaps I missed it, but I didn't see adaptive optics, and I think that's not there because of probably all three of the design characteristics, depth, speed, and width.
Yeah, so the question was that the gentleman noticed that there was not adaptive optics on this telescope. And for those that don't know, adaptive optics is very rapidly deforming mirrors that allow you to compensate for the turbulence and distortions of the light as it passes through the atmosphere. And the primary reason why we don't have adaptive optics in our telescope is that when the telescope looks up through the atmosphere, if the field of view is relatively narrow, right, it's the same patch of atmosphere that you see. But as that field of view gets wider, it's a different patch of atmosphere. And so it's what we call it loses coherence, and so that a single deformable mirror cannot correct a wide field of view. And so it becomes what we call a seeing limited telescope. So it's basically the wide field of view that prohibits us from doing adaptive optics. Yes, ma'am.
Do you have any environmental or ecological opposition? I know we get on my those sort of problems.
So the organization where we are putting the telescope owns the land, and it's a very large portion of land, and it's actually been designated as a scientific reserve, which is all very helpful. And we go through the very normal environmental impact statements and environmental impact assessments. We went through all of that, had no opposition from any of the 17 different organizations that get involved. And so in this particular case, we had a very smooth process through the environmental.
Why Chile? Why that spot?
Wow, there's that's not an easy question to answer because there's a lot of different answers. I think one of the answers is what Victor just mentioned just now is we we own a piece of property where this telescope is being built. There are already telescopes there. There's two mountaintops in this property. One's called Cerro Pachón, the other one's called Cerro Tololo. Cerro Tololo's been operating telescopes for 50 some odd years. Cerro Pachón is a little bit newer. So all the infrastructure, roads, power lines, communications, all that stuff is already there, so we didn't have to develop a new site. That's sort of a programmatic reason why we went to Chile. Scientifically, when you look out at the night sky, you know, the distant universe is the same no matter where you look. So from a cosmology point of view, there's not a real preference to be in the northern hemisphere versus the southern hemisphere. And then lastly, Chile, the northern parts of Chile have this wonderful reputation of being dry, which also means they are clear. They have a lot of usable nights. Yes, sir.
Is the CCD array cooled?
Yes.
To increase sensitivity?
It's cool for not to increase sensitivity, but to decrease its noise. Right? There's thermal noise in the silicon that makes up the CCDs. Also, because of minor defects within the silicon lattice, you get defects. And cooling the CCD reduces the impact of those defects to the point where they practically disappear. Any other questions?
We can keep taking questions, but I'm going to ask that we actually have some other videos that can be running in the background. That shouldn't be too disturbing, but give you a little bit of other context.
Well, all engineers and scientists run into budget limitations, and you have imagination stretches well beyond budget limitations. So what would the team do with more money? In other words, what are you going to do iteration upgrade?
That's my program officers over here. We have exactly enough money to do what we said we were going to do exactly enough time. We have a list of things that we would do differently if we are fortuitous enough to have some things go well. And for the most part, mostly what we would do is do things that would lower the risk, would give us a little bit more robust time to test and a little bit more time to characterize, so that when we turn it over to the operations team to run the survey, we'd be a little bit more sure about how it would behave. So that's sort of the programmatic answer to what we would do, because we spent a lot of time deciding what was a sufficient budget to build what we were going to build. And then the operations team, it's a little bit money limited, but we have to operate every night and take so many people, and in fact that proposal just went in. And so I think there's nothing that I would say, oh, this is what's failing us, this is why we need more money. Maybe I would say engaging and getting people prepared for what it will take. Maybe Chuck will say a few words about that.
Yeah, I was going to add to that, looking a little further into the future, right? Because LSST is built to conduct a 10-year-long survey, but it's quite a machine that we're building. And so in the United States here, we go through something called the National Academy of Sciences, and they sponsor what we call a decadal review, where that decadal review process solicits ideas from the scientific community about what is it that the community believes is the most important questions that need to be addressed, and what are the necessary experiments or new programs that should be done to answer those questions. And so it's interesting that here we are at the 2017, and that process, that decadal review process for 2020 is just getting underway now. And so if there is sufficient justification and interest by our community to do something beyond 10 years, then that will be reviewed and evaluated through this process, and then it will get looked at against other proposals and prioritized.
Under the facility that's there,
just the telescope. What's the rest of it for?
So that's for a lot of the infrastructure required just to maintain the camera and to maintain the optics. And there's a control room where we can control the entire facility. And then below that, there's all the chillers and mechanical equipment necessary to provide the utilities for operating.
That's fine.
It's like NASA, I mean, this is a U.S. project, and therefore it's the United States information. I mean, are other people, like, how that should be shared?
So this is a U.S. federally funded project. It is open to the entire U.S. population, all scientists equally. Because we are in Chile, we've also made it completely open and available to the country of Chile. And we are taking international partners or international contributors who are participating in the actual funding of operations. And they, as individually named scientists, can also join. But the APO part, the parts that we make available through the portal or just general public use, which is a somewhat limited version of all of the data, is available worldwide. Other questions?
If not, thank you all for your attention.